Hello everyone, welcome to the next lecture on MOSFETs. Okay, so let me give you a very brief, a few minutes, 3 to 5 minutes introduction, not introduction, kind of a summary of what we have talked about so far. Okay, so we started with the structure of the NMOS, right? Source terminal, gate terminal, drain terminal, gate electrode, heavily doped N-type regions for the source and the drain, and P-type body. So the majority charge carriers over here will be electrons, and over here it's all filled with holes. Okay, so that's the basic structure. So the first thing in order to operate the transistor, we create a channel. We also connect the body terminal to the source, or over here we also ground it and connect it to the source just to reverse bias or cut off the two PN junctions in between source and the substrate and the drain. Okay. So in order to operate the transistor, the first thing is to create a channel. And in order to create a channel, we have talked about this now so many times. We start with a gate to source voltage. We apply a gate to source voltage. So a positive voltage appears over here on the gate electrode. It will push down all the holes in the body to create a depletion region. So this channel region will be empty of the charge carriers. Then we have a lot of these free electrons here in the N-type source and the drain. They will be attracted over there, and it's all filled with electrons. So we ended up creating or inducing a channel, and we ended up inducing an N channel. So this is why it is called as an NMOS. Today we are going to talk about a PMOS as well. Okay, so the second thing after that we do is we apply a drain to source voltage. So when we apply a drain to source voltage, an electric field will be established in between source and the drain, and this will provide a current flow. So all of these electrons will start to flow towards the drain terminal. And so our drain current will be from drain to the source, opposite to the flow of electrons. So this is what we talked about. We also saw that it behaves like a parallel plate capacitor, and the conductance of this parallel plate capacitor depends on a few factors. One is the amount of the voltage that we have applied over here. It also depends on the aspect ratio of this channel. The aspect ratio was W over L, the capacitance of the oxide layer, and the mobility of the charge carriers. Over here it's an NMOS, so mobility of the electrons. Okay, so we ended up deriving this equation for the drain current for an NMOS. And we saw that for a very small values of VDS, our channel behaves as a linear resistance, right? And the conductance of the channel depends on these three factors: mu and Cox, W over L, and VOV. And the resistance of this channel, RDS, is equals to 1 over GDS. Okay, these are capital DS. Okay. We also talked about that this mu and Cox is called as a process conductance parameter, and the product of the process conductance parameter and the aspect ratio W over L is called as a MOSFET conductance parameter, Kn. So just remember these notations. Okay, then we talked about this IV characteristics. When the VDS is small, when the gate to source voltage is less than the threshold voltage, nothing will flow, no channel will be induced, and it is irrespective of how much drain to source voltage that is applied, no current is going to flow. Now, as soon as the overdrive voltage or the gate to source voltage will increase, the current will start to flow and it will increase. So increasing the overdrive voltage or gate to source voltage will increase the conductance of the channel, or reversely, it will decrease the resistance of the channel, right? So your current is increasing like this. Okay. We also talked about this is what happens when the VDS is small. What will happen when the VDS is no longer small and it increases? When the VDS increases, if we look closely at the source end, our voltage that appears at the source end is equal to VGS. And the voltage that will appear at the drain end or gate to drain voltage is equal to gate to source voltage minus drain to source voltage. So even when even in the earlier case, when we were assuming that the channel is uniform, this drain to source voltage was appearing there, but it was very small that we ended up neglecting it. However, now when it increases sufficiently larger, comparably larger as compared to the gate to source voltage, we will see that the voltage at the drain terminal will start to decrease as compared to the source terminal, right? Because it is increasing from 0 to VDS here, like this. Okay. Now, when that happens, we also saw earlier that the depth of the channel depends on the voltage that is applied. Right, so voltage over here at the drain terminal is less as compared to the source, so that is why the channel ends up being tapered. So we discussed all of that, then we ended up deriving these more detailed IV characteristics. Again, over here, our gate to source voltage is greater than the threshold voltage for all of this conduction to occur. So we assume that in this smaller region, our relationship is a linear relationship and channel is a linear resistance. And VDS is small. And we can see over here, right? So this is the very small values of the VDS. Now, as soon as we will start to increase the values of the VDS, the resistance no longer remains constant or a linear resistance. It will start to increase. And as the resistance is increasing, the current will decrease. So the current will start to saturate as the VDS is increasing. And a point will come at which the value of the VDS will become equal to the overdrive voltage. When that point comes, the channel over here gets pinched off over here. So it will hit this point. At this point, the current does not stop to flow. It will still flow. However, it will remain constant. In the next lecture, we will discuss more that actually that is not entirely true, that even the current does not remain constant, it will still change. We are going to discuss that in detail. For now, just assume that it remains constant, one step at a time. Okay, so we will get a constant current. So this region is known as a saturation region. This region is known as a triode region. This small region is also part of the triode region, but it is called as when the channel say behaves as a linear resistance. So in this entire triode region, our values of the VDS is less than the overdrive voltage. And in this entire saturation region, our values of the VDS is greater or equal to the overdrive voltage, right? So take this equal signs out from here. Okay. Okay, so this is good. We discussed that. We also saw that the equation, the drain current equations for the triode region, especially for this region, we initially ended up driving an equation for this, right? So the equation for this triode region and the saturation region is going to be different. So we ended up driving it. We saw that rather than having a uniform channel, now we have a taper channel. So we saw that the average voltage on the taper channel is equal to VOV minus half of VDS. So we ended up replacing this value and ended up driving a new equation. So this is the equation, a more comprehensive equation for the drain current. Further, we saw that for the pinch off, what will happen is at the pinch off, our drain to source voltage will become equal to the overdrive voltage. So we can replace this value in the earlier equation. And if we will replace that, this is a drain current value for our saturation region. So it's good to remember all of these equations, or not remember, but at least understand these equations. You will, in the exam, we will allow you to have these equations in handy. Either, we can discuss the details. But these equations, you can have these equations. Important thing is to understand these equations here. Okay. So bottom line over here is that our channel can operate this kind of this curve, right? It can be operated in three different regions. One is a cutoff region when VGS is less than the threshold voltage, so nothing is flowing. Then we have a triode region in which VDS is less than the overdrive voltage, and then we have a saturation region in which VDS is greater than the overdrive voltage. Okay. So in the lecture today, we are going to do one quick example. We are going to discuss something more, a little more about the NMOS, and we will also talk about the PMOS. Okay, so let's do our one example today. Okay, so let's consider there's an engineer who is trying to design the circuit application and is fabricating a transistor, and the equipment they have, it can do the cell minimum. Remember that the cell minimum is the smallest length of the channel that can be fabricated by a particular equipment being used in the fabrication facility. Okay, so this L minimum is 0.4 micron. We have an oxide layer thickness, 8 nanometers, mobility of the electrons, and the threshold voltage, 0.7 volts. Okay, so what we need to do, so the first thing that we need to do is to find out the oxide capacitance and the process transconductance parameter. So we know that Cox is equal to epsilon ox over T ox, right? So our epsilon ox is depends on the material of the oxide. And let me repeat here, if I do not specify, or an example problem does not specify, for the sake of this course, does not specify the material, you can assume it to be silicon dioxide, right? Earlier we have calculated the value of epsilon ox. Let me go back and show you that value. I think it was probably in one of the first lecture. Yeah, okay, right. So capacitance oxide is this permittivity and the thickness of the oxide layer, and here is the value of the 3.9 times epsilon naught. So this is the value of the epsilon ox that we can use. Okay, so we are here, so we can use that epsilon ox value from there, and we can calculate the Cox value. Okay, the other thing that we need to find out is Kn dash. So our Kn dash would be equal to mu and Cox. So Cox is going to come over here, mu and values will come from here, so we can easily find out the Kn dash too. Here are these calculations, right? So Cox is epsilon ox over Tox. The value comes from the earlier slide I showed you. And this is a thickness. We can easily find out these values. Process conductance is mu and Cox. This is the mobility of the electrons. It's an N channel, so charge carriers, they are constituting the current and electrons. We have a capacitance of the oxide layer. So we ended up finding out these values. You can calculate that. Okay, so other part of this problem is, okay, so now we are given the aspect ratio of that MOSFET as well. So for that MOSFET, our ratio of the width to the length of the channel is this, 8 microns to 0.8 microns. And we need to calculate the values of the overdrive voltage, the gate to source voltage, and the minimum drain to source voltage. We're going to come back to this minimum point here. And yes, we need VDS min needed to operate the transistor in the saturation region with a DC current of 100 microns. And now this is important point over here, that so one of the things that you are going to realize while solving a lot of these problems is it is always very important as a first step to find out in which region the transistor is operating. And in this example, they are already providing you that information. The transistor is being operated in the saturation region. So we know that if the transistor is being operated in the saturation region, our drain current remains constant. So that is why it's a DC value. 100 micron amperes. So in order to find out all of these voltage values, we can start with the equation of the drain current and the saturation region. So equation of the drain current in the saturation region is over here, this one, right? In the pinch off when we talked about. So half Kn dash W over L VOV whole square. Right, so our drain current equals half Kn dash W over L VOV whole square. Now we know the value of ID. Kn dash is coming from here. W over L is over here. And we can easily calculate the value of the overdrive voltage, right? So once we find the value of the overdrive voltage, and here are the calculations you can find out. Okay, so once we find the value of the overdrive voltage, we know that the gate to source voltage, right? So what was overdrive voltage? Overdrive voltage was the excess of the gate to source voltage beyond threshold voltage. So gate to source voltage will be equal to threshold voltage plus overdrive voltage. So it will be 0.32 plus 0.7. So we can easily compute the gate to source voltage. All right. Okay, so the gate to source voltage is 1.02 volts. Okay. So the third thing that we need to determine is the minimum value of the drain to source voltage that is needed to operate the transistor in the saturation region. So over here we are talking about the starting point of the saturation region, right? So we saw that in this IV characteristics, we saw that exactly at this point our saturation region starts, or this is the smallest or the minimum value of the drain to source that is needed to operate the transistor in the saturation region, and this value is equal to when drain to source voltage will become equal to the overdrive voltage, right? So in this problem we need to find out the minimum drain to source voltage that is needed to operate the transistor in the saturation region, which is equal to the overdrive voltage. So VDS minimum is equal to the overdrive voltage. Okay, so we ended up finding this out as well. This was overdrive voltage. Okay, now for the C part, we have a similar device as talked in B, and now we need to find out the values again of the overdrive voltage and the gate to source voltage. But now our device is being operated as a 1000 ohms resistor for a very small value of the VDS, right? We talked about when the VDS is small, channel and or the MOSFET can operate as a linear resistance. And when this is the case, we saw that this is going back on the IV curve. This is the small region of the device, right? Okay, and we also calculated the value of the resistance here in over here. We find out the values of this resistance. This is the conductance of the channel, and resistance is opposite to this channel, right? So the resistance will be opposite to the conductance, or one inverse of the conductance, 1 over mu and C ox W over L, and the overdrive voltage. Okay, so let's go back to the slides here, right? Okay, so we know that RDS equals to 1 over mu n C ox W over L VOV. We need to find out the value of the overdrive voltage, right? We need to find out VOV. So VOV can be found out by using this resistance value here. We already know mu and C ox from the earlier A and B parts, and W over L as well from the B part. So we can easily compute the value of the VOV. And once we find the value of the VOV, we can easily find the value of the gate to source voltage too, because gate to source voltage is equal to the overdrive voltage plus the threshold voltage. So you just need to add 0.7 to this. Okay. So here is the value of the RDS. This one, Kn dash is coming from the last B part, W over L from the B part. Overdrive voltage can easily be found out by this, and then you need to add 0.7 VT to this thing to find out the value of the gate to source voltage. Okay, so again, a hint, an important thing while operating these transistors or while solving these problems is to figure out in which specific region the transistor is being operated at. So the concepts are really the key here. Understand the basic concepts, right? And you can always go back to this curve. In today's lecture, I'm also going to give you kind of a summary slide for the formula that you can use to kind of find out, to solve most of the problems, if not all. Okay, so this is what this problem is. Let's talk about another brief concept here before moving forward. Up till now, so the concept is about operating the transistor in the subthreshold region. So what is the subthreshold region? Up till now, we have been saying that when the gate to source voltage is less than the threshold voltage, the drain current is 0. And why is that? Even though the VDS is applied, even though we have applied the VDS, but if the gate to source voltage is less than the threshold voltage, the drain current will be 0. And why? Because no channel is induced. We have been constantly saying that over the last many lectures. This is not entirely true. Yeah, so if you remember, if we can make some, so just to understand the basic concept of this semiconductors and the p-n junctions, you can make kind of a similar, you have seen the similar story in a diode, or a p-n junction of a diode, right? You have discussed different models of the p-n junction of the diode when you have a current and a voltage for a diode, right? And you have seen that you have seen a constant voltage drop model, and you have seen an exponential model, right, in which the current will start to increase exponentially at a specific point. Okay, right, and this is a real model, right, and this is just a simple model to solve most of the circuit problems. Okay, so more importantly, similar is true in the operation of the MOS transistor. Again, these are the p-n junctions and again the semiconductor devices, that when the gate to source voltage is less than the threshold voltage but very close to the threshold voltage, it is not necessarily true that the channel is not induced or the current is zero. A very small amount of the current will start to flow. That will exponentially increase as the gate to source voltage approaches to the threshold voltage. The current will exponentially increase, and this region is known as a subthreshold region. It's just a smaller concept. However, for most of the exam problems, you can assume that when the VGS is less than threshold voltage, the current is zero. However, it is important to give give all the necessary information, or more importantly, to understand the basic concept that even in the subthreshold region, we have seen that while even studying the diodes, that it is not entirely true. The constant voltage drop model of the diode is not entirely true, and the exponential model is real. So something similar is also true in the case of a MOS transistor, that your current will start to flow when the gate to source voltage is less than the threshold voltage, but is very close to the threshold voltage, right? Provided that the VDS is applied to provide a path for the current flow, and then the current will exponentially increase as the gate to source voltage approaches the threshold voltage here. Okay, so this is what we talked about. Earlier we have talked that the gate to source voltage less than the threshold voltage, nothing is flow, the device is cut off, which is not true. When the VDS is smaller but close to VT, a small drain current still flows. And this is called as a subthreshold region of operation, in which the drain current is exponentially related to VDS. Okay, so this is kind of a smaller important concept, but for the purposes of the exam problems, if it is not unspecifically specified, then you can assume that if your gate to source voltage is less than the threshold voltage, you can ignore the subthreshold operation of the transistor, and you can assume that the drain current is equal to zero. Okay. So let's very quickly, over here we are going to look at the symbol of the MOSFET, and we are going to talk more about the current and voltage characteristics in more detail in today's lecture before moving to the PMOS. Okay. So in this chapter we are mostly going to talk about this DC operation of the MOSFET, and we will also do some of the examples. However, for the high frequency operation of the transistors is also discussed in chapter number 10. We will not cover that chapter in this course, and that will be covered in most probably in the digital electronics course. So stay tuned for that. Okay, so importantly, so let's find out the symbol for the NMOS and the PMOS later part of the lecture today as well. So why the circuit symbols are important, you guys already know that when we make all of these electronic circuits, it's really important to have a symbol, because this serves kind of as a representation, right? We have a diode symbol, a resistor symbol, capacitor symbol. So similarly, we need to have a symbol for these MOSFET as well. Okay. So for an enhancement type MOSFET and an N-channel enhancement type MOSFET, the symbol looks something like this. Let me do one thing here. Okay. So this is a symbol of the N-channel MOSFET, and we are going to kind of simplify the symbol, and we will see what is a symbol that is mostly used in the literature, or in the problems, or in the circuits that you usually see, but it's the most detailed symbol. Okay, again, 4 terminals: drain, gate, source, body. This is the gate terminal, and you can see that this is a gate electrode. This is here's a small separation, which is the oxide layer, and then here's a channel. This darker line over here is a channel, right? And this inward arrow is a representation of the inward arrow on the body is a representation of an NMOS here. We will realize that when we talk about the symbol for the PMOS, the arrow will be outward, on the body terminal. Okay, right, so we have two vertical lines, one for the gate, one for the channel. This just shows, yeah, this shows that the gate electrode insulated from the body of the device by the oxide layer. Okay. Okay, so more importantly, as you will realize in the later part of these chapters as well, and whenever we will discuss more about the MOS transistors, that usually we do not include the body terminals, and you may have realized that as well while discussing most of the operation of the MOS transistors, that we ended up either connecting the source terminal, the body terminal, to the source terminal, or putting it to the most negative supply. We will discuss this negative supply concept in more detail for NMOS. Okay, so more importantly, the three most important terminals for the NMOS are gate, drain, and the source. Yeah. Okay, so this means that if I have to simplify the symbol, I can take out the body terminal. So the problem is, if I take out the body terminal over here, then I cannot differentiate in between the NMOS versus the PMOS, because this arrowhead here is something that was differentiating in between an NMOS versus, we will see in the PMOS as well. So what we can do here is we ended up putting an arrow on one of the other three terminals, right? So we ended up putting an arrow on the source terminal. So always remember that we will put an arrow on the source terminal, and the direction of the arrow represents the direction of the current flow. For an NMOS, we saw that the drain current flows from the drain to the source, right? So the drain current is flowing something like this. So this is a drain current. So drain current is flowing from the drain to the source. That is why this arrow is outward. So this outward arrow means that this is an NMOS. So even if these symbols are not there, you can still figure out what these symbols are, right? So this separation of these two, of the electrode and the channel, is a gate terminal. Wherever you will see an arrow, it's a source terminal, and the remaining terminal is a drain terminal, and body terminal is usually not shown, right? So this is a more simplified representation of the NMOS transistors, and you're going to see this thing more and more often in the circuit examples that we will do. Okay, so let's talk more about it in terms of its operation. So NMOS transistor can be operated in three possible regions. So one is a cutoff region, right? VGS is less than VT, ignoring the subthreshold region. The triode region, right, when VDS is less than overdrive voltage, and the saturation region when the VDS is greater or equal to the overdrive voltage. So transistor can be operated in three separate regions. And we will discuss two specific examples or operations of the transistors in this course. One is as transistor as a switch, and other is transistor as an amplifier. And we will see that when we operate the transistor as a switch, we can utilize this cutoff region and the triode region. So initially the transistor is cut off, it's off. As soon as we will induce first channel, and then as soon as we will give a small VDS value, the transistor will be turned on. A lot of current is going to flow. And the drain current is going to flow, right? And then we will also realize that when we have to use MOSFET as an amplifier, we will operate the transistor in the saturation region. And these things, because for the amplifiers, we want to provide a constant current to the load. So that is why we usually operate the transistor in the saturation region when the MOSFET is being used as an amplifier in the design of an amplifier circuit. Okay, we will discuss this amplifier design in many lectures subsequently in the next week. Our next week is going to be focused on how we can design these MOS amplifiers based on the NMOS and the PMOS. So we will discuss more things there, and these details will be more clear. Okay, so here's a summary slide I was initially talking about. So this summary slide is, yeah, it's kind of everything that we have talked about, including all the important equations that you need to solve the circuits and the examples. So let's very quickly go through this slide so you know all the details there, right? Okay, so here's the circuit symbol, right? No indication of the terminal, so we know that this is a drain. We know that the arrowhead is on the source, and the remaining one is a drain. Here's the drain current from the drain to the source. Looking at the arrowhead, I know it's an NMOS. Okay, so I will apply a gate to source voltage, right, in between the gate and the source terminal. Then I apply a drain to source voltage in between the drain and the source terminal. I kind of bias this transistor. Okay, so we know that when the gate to source voltage is less than the threshold voltage, no channel is induced, transistor is cut off, and drain current is zero. We discussed that multiple times. Now, as soon as we will apply that, channel will be induced, and as we vary the drain to source voltage, this is iD-VGS characteristics that we get. This is when this line is when the channel is off, VDS is less than VT. Now, as soon as the VGS increases, initially over here we have a linear resistance, and which is represented by this. Now the resistance will start to increase and the conductance will start to decrease until a point comes when your VDS is equals to VOV. At this point, the transistor enters into the saturation region and we get this, right? So all the information is kind of written over here in the slide. Now, okay, so in terms of operation, you can see that in the cutoff region is this region, VGS is less than VT. For the other two regions, the triode region and the saturation region, all the equations are written here. Here's the triode region, here's the saturation region. Okay, so for the triode region, we know that the drain to source voltage is less than the overdrive voltage, and for the saturation, greater or equal to the overdrive voltage. So we can see that less than the overdrive voltage, greater or equal to the overdrive voltage. Or the gate to drain voltage is less than the threshold voltage, and the gate to drain is, sorry, over here in the triode region it is greater than the threshold voltage, and over in the saturation region it is less than the threshold voltage, right? So what was the gate to drain voltage? The gate to drain voltage was equal to gate to source voltage minus drain to source voltage. So this was what we were saying, that this is the voltage that appears in the drain terminal, right? So for the triode region, this VDS in this portion, it is very small, and that is why we were ignoring that, but it was still appearing there. However, when it becomes sufficiently larger, as it approaches equals to the VGS, or more importantly VOV here, it will be pinched off, or the channel over here will move from constant rectangular channel to a trapezium. At the saturation, it will be pinched off. Exactly, becomes kind of a triangle here. Okay, here are the equations that are relevant for this. Over here, for example, this is the equation for the drain current for the saturation region. Here's the equation for the drain current for the triode region. So this slide provides kind of a very good summary and all the relevant information and equations at one place. And I think if you understand all the basic concepts, then this one slide should be enough in terms of providing you all the necessary information to solve most of the examples and or even answer some of the basic conceptual questions. Now let's look at the characteristics in more detail. And we have been discussing this characteristics multiple times. Again, we can briefly talk about it. Here is the drain to source voltage. Here is the overdrive voltages. Okay, so sorry, over here we have a drain to source voltage, over here we have our drain current, right? And we have kind of evaluated these IV characteristics. Over here, our gate to source voltage is less than the threshold voltage, so we are cut off, and then we have these equations in which this region of the equation is a triode, and then this part of the figures is a saturation region. As we are increasing the overdrive voltage and in turn the gate to source voltage, our drain current is increasing, right? So another important thing that we can see over here is this characteristics. More importantly, and we are going to talk more about this, the characteristics of the drain current to the overdrive voltage, right? So this is the VGS, or the overdrive voltage. As we are increasing the overdrive voltage, right, the drain current is exponentially increasing. So we can see that if we will apply a constant drain to source voltage and change the overdrive voltage or the gate to source voltage, our current will increase. So we are going to talk about this characteristics in more detail. Let's look at that in the next slide. Right, okay. So this has to do when the transistor is being operated as an amplifier. So as an amplifier, we can operate the transistor in the saturation region. We're going to talk more about that. We're going to cover the very basic or introduce the concept here, and then we are going to dedicate another 3 or 4 lectures starting next week on the MOS amplifiers. Okay. So we saw that in the last figure that in the saturation region, or right at the start of the saturation region, once the drain current remains constant, but the value of the drain current, what is that constant value of the drain current, can be changed by changing the value of the gate to source voltage, and it is independent of the VDS, right? So let's go back here, and we see that, right? So our drain current is constant over here, right? So depending on, so I can control the value of the saturation current or the drain current here by changing the value of these overdrive voltages, right? So my saturation current ID depends on the value of the gate to source voltage that I apply, or the overdrive voltage that I am applying beyond the threshold voltage. Okay. So that's an important thing, and that is independent of the VDS. Irrespective of whatever VDS you provide, once the transistor enters into the saturation region, the current will remain constant, right? And that current, that constant current, is determined by the gate to source voltage or the overdrive voltage. Okay, right? So this is the characteristic that we have seen, right? Less than the threshold voltage, our current is 0. The ID current is 0. We know that this is not entirely true due to the subthreshold region, but for simplicity, we can assume it to be true. And our current is 0. Okay, so as soon as the drain to source voltage is greater than the gate to source minus threshold voltage, this means that it is being operated in the saturation region. We can plot a drain ID to the VGS characteristics, which means that we are going to have our drain current, the value of the drain current is directly proportional to VGS, or the gate to source voltage. Okay, and interestingly, you can see that it is not linearly related. We are going to talk about this concept in much more detail while designing the linear amplifiers. So what we can do is, for example, we know that the current can be constant, so we can apply the input signal at the gate to source voltage, and as soon as it will increase a specific threshold voltage, a drain current will start to follow, and that will depend on the amount of the voltage that is applied at the gate terminal. So we can build these voltage amplifiers. Okay, so we are going to talk about that in the next lecture in more detail, right? So another important kind of concept here is that while operating the transistor in the saturation region, is that we can operate the transistor as a constant current source, right? And the value of that is determined by the VGS. Now going back to the other figure, we can see that, right? So for a specific value of the VGS, we can operate the transistor as a constant current source in the saturation region. So this is a saturation region, constant current, constant current, constant current, constant current, right? And the value, whether the transistor have the constant current of this value, this value, this value, or this value, this depends on the overdrive voltage of the gate to source voltage. So transistor can be, or a MOSFET can be operated as a constant current source, and the value of that constant current is determined by the gate to source voltage. So we can say that it is a voltage controlled current source, right? And this is a relationship that we have derived earlier. This is an equation for the saturation current of the ID, right? So this is this ID. So ID equals half of Kn dash W over L or VOV, and this VOV is essentially, we know that VGS minus VT. Okay, so with that, this operation of the transistor as a current voltage control current source is an important concept, and I hope you will understand that. And this concept is going to come in handy, and we will discuss this concept again and again in much more detail again when we will talk about MOS amplifiers starting next week. Okay, so finally let's start with P-channel MOSFET, or commonly known as PMOS. So up till now we have been discussing about the NMOS. So let's talk about the PMOS. Okay, so in the PMOS is very similar in operation as the NMOS. The only thing that is reversed is that we essentially, rather than having a P-type substrate, now we are going to have an N-type substrate. Rather than having an N-type source in the drain, we're going to have a P-type source and drain. And we will see that now in order to operate the PMOS in the same way as we have operated the NMOS, we needed to reverse the polarities of the batteries too. Otherwise, the operation is pretty much the same. Okay. So we have a substrate and the body is N-type, source and the drain are P-type, right? So this is an opposite to the NMOS, where source and the drain were N-type or N-positive, heavily doped N-types there. And the substrate in the body was P-type for the NMOS, right? Okay. NMOS and the PMOS are also called complementary transistor. By now you have already realized that because of this complementary nature of this source, drain, and the substrate regions. So here's the structure of the PMOS, right? You have a body terminal, you have a source, gate, drain. Structures remain the same. You have a P-type, N-type. In an NMOS, we have again an N-type source, N-type drain, P-type substrate. In a PMOS, it's complementary, so P-type source, P-type drain, and an N-type substrate. Okay, so the operation of this transistor is going to be pretty much very similar. Now we know that for a P-type, for an N-type substrate, we are going to have a lot of these electrons here, right? Majority charge carriers for the N-type. Over here, we're going to have a lot of holes. So as soon as we will apply a gate to source voltage, now, if you remember, for an NMOS, we ended up putting a positive polarity on the gate electrode. Now we need to, why we did that? Because we want to push all the holes down. Now we want to push all of these electrons down, right? So what we ended up doing is we ended up connecting the battery in opposite. So we ended up creating this negative charge over here on the gate electrode. This pushed down all the electrons down, and we ended up creating a depletion region. So all of these holes will be pulled here. So we ended up creating this P channel, right? So that is why it is called as a PMOS. So in an N-type substrate, we ended up creating a P channel, so a PMOS. Remember this inversion layer concept that we talked about earlier in the first lecture. Okay. So as soon as this is done, we connect our drain to source voltage and the current will start to flow. Important thing here is drain to source voltage is also in opposite polarity. Now we ended up creating, we wanna create a current flow. So in order to do that, we connected the battery in opposite polarity. So we have a negative here. Now all of these holes will be attracted, right? So all of these holes will attract over here and our current will start to flow from the source to the drain. And so important thing is our drain current over here will be in the direction of source to the drain. This is an opposite to the NMOS, where the current was flowing from the drain to the source. Okay, so operation is pretty much the same, right? So I hope you will see that the differences are only the regions are complementary and the batteries are in opposite polarity. Right, so we talked about this. Okay, so in order for the PMOS to be operated, right, we want to make sure that this voltage VGS, it needs to be greater than the threshold voltage, right? However, since we have this over here, so this VGS here, since it's a negative polarity, so we want to make sure that our VGS here, so this specific VGS, it needs to be less than the threshold voltage, because our threshold voltage now is minus, let's say, 0.7 as an example. So we want to make sure that our VGS that comes over here as a negative polarity is going to be less, say, minus 0.8, minus 0.9. Or in simple words, we are going to realize that just to make things more compatible with the equations and more similarity with the NMOS as well in terms of equations, and to stop this confusion of the negative signs, we are going to create this modulus of the magnitude of these voltages. And so when we do that, we will see that our mod of the gate to source voltage should be greater than the threshold voltage, so that our overall concept is the same, and then we are just using the modulus values. Okay, so right, so our gate to source voltage is should be less than the threshold voltage, because our threshold voltage is now negative. So in order to and we connect the battery opposite, right, so our gate to source voltage should be more negative or greater negative as compared to the threshold voltage, right? So we talked about this, or just to avoid the confusions of this negative signs, we can just use these mod values. So our mod of the gate to source voltage should be greater than the mod of the modulus of the threshold voltage for the PMOS. Right, we talked about this, that negative VDS, again, a battery in the opposite polarity is needed to cause a drain current to flow. And the drain current is because of the holes rather than electrons. In the n-channel MOS, it was, or an NMOS, it was due to the electrons. Now it is because of the holes. So the process transconductance parameter for the PMOS device was, so if you remember, so this was for the NMOS. Now we are going to change it to Kp dash equals to mu, rather than mu n, we will write mu p C ox. Okay. Oh, yeah. I think, yeah, I realized that. Okay. So it's mu, Kp dash is mu PC ox, mobility of the holes and the oxide layer, capacitance. So important thing is the mobility of the holes, another important concept. Mobility of the holes is smaller as compared to the mobility of the electrons. We touched upon that in one of the lectures earlier. And the mobility of the holes, or the mobility of the electrons, is at least 2 to 4 times higher as compared to mobility of the holes. So mobility of the electrons is greater than mobility of the holes, right? And then we can also find out the transistor transconductance parameter, Kp equals Kp dash W over L. Okay, so NMOS and the PMOS. So when these MOS transistor came into being initially, due to the slight ease in fabrication, PMOS transistor were more widely used. However, when the NMOS fabrication challenges were solved, due to the higher mobility of the electrons, NMOS are more widely used now. And the main reason, again, we discussed that electron mobility is 2 to 4 times more higher, resulting in more higher operational speed of the transistors. Let's discuss another brief concept on complementary MOS, or a CMOS. And this is going to be a very important. We are going to just talk about the CMOS in one slide today, and this is it. But you're in the next course of digital electronics, you're going to discuss a lot about the CMOS, because we make a lot of these processing circuits based on the CMOS technology. Okay, so what is CMOS? CMOS is complementary MOS that will use both NMOS and the PMOS in the same chip, right? And it is the most commonly and most dominant MOS technology that is used currently. Okay, so this is how a PMOS looks like. So you do realize by looking at the picture, even without looking at the picture, what the challenge is. The challenge was, or the challenge is, that for an NMOS, our substrate needs to be a P-type body. For a PMOS, our substrate needs to be a N-type. So how you can put both of the NMOS and the CMOS on the same chip? Sorry. Okay. Right, for the NMOS, okay, so let's discuss one transistor at a time. So right, so for the NMOS, we have a N-type source, N-type drain, and a P-type body. Okay, so NMOS is good. Let's talk about the PMOS. For the PMOS, we have a P-type source, P-type drain, and we need an N-type body. So what we do is we initially create this well, an N well, in the P-type body, and then make these P-type source and the drain regions over there to make a PMOS. So our main body will remain the P-type for the NMOS, but for the PMOS body, we create an N-type well to make a PMOS on the same chip, to make this a CMOS structure on the same chip, okay? And both the CMOS and the NMOS are separated by this silicon dioxide isolation layer. Okay, we talked about this. PMOS is fabricated in a specially created N region known as an N-well, and they are separated by thick oxide layer, which serves as an insulator in between the two transistors. Okay, so very quickly, let's talk about the symbol of the PMOS. Again, the concept is very similar to what we discussed in detail for the NMOS. Here's the most detailed one. We have a gate, source, and the drain. The gate representation is because of these two things. This is a channel. Here's the gate electrode, and this spacing is oxide. When the arrow is outwards, this means that it's a PMOS. For an NMOS, this body arrow is inwards. But for the most simplistic models, for the simplistic symbols, we don't use a body terminal. So we take this body terminal out, and then we ended up putting an arrow on the source terminal, right? So we saw that in the source terminal, our drain current, where should the arrow be? The arrow should be on the source terminal, and the direction of the arrow should be based on the direction of the current. And in the PMOS, we saw that the direction of the current is from the source to the drain. So the direction of the current is from source to the drain, right? So yeah, this is ID. Again, so the important thing is two things to remember here. So one is wherever the arrow will appear, that's the source terminal, and the direction of the arrow will tell you the direction of the current and what exactly, whether it's a PMOS or an NMOS. For an NMOS, the direction of the arrow on the source terminal is outward because the current flows from the drain to the source. In an PMOS, the current flows from the source to the drain, so the direction of the arrow is inward. Okay. Similarly, over here, we have a summary slides for everything related to the PMOS, all the operations, all the characteristic curves that we have talked about is exactly the same. So we are not going to repeat that. Right, so here's a symbol. We have a gate, we have a source, we have a drain. So we connect this battery, kind of over here we show it as a positive source to the gate battery, in which again we apply this negative voltage to the gate electrode, and then we apply a negative voltage to the drain terminal as well. So here is how we bias this transistor, and then we saw that, or we know that whenever it is less than whenever the mod of the voltage that we apply over here is less than the threshold voltage of the p-type material here, no current will flow and our drain current will be 0, right? So VTP is by convention negative. And as soon as we will apply as soon as it will be more than the threshold voltage, the mod of the gate to source voltage or the source to gate voltage is more than the threshold voltage, it will current will start to appear, a channel is induced, and with application of the source to drain voltage, a current will flow. So we ended up developing these characteristics. Now you will realize that everything else is the same. Over here, no channel will flow, no current will flow, no channel exists. Then the channel is induced, and we can divide that into the triode region and the saturation region. All the relationships are the same that we want to, for example, for this voltage, so this source to drain voltage should be equal to the overdrive voltage for the for it to enter into the saturation region, right? So this is the entry point of the saturation region. Less than that, it is in the triode region. More than that, it will be in the saturation region, right? So the only distinction to note over here is that modulus sign, right? So if you will replace, going back to the NMOS slide, right? So essentially what you ended up doing is on this gate to source voltage values, now we are using this modulus values, and we ended up reversing the polarity of the drain to source and the gate to source, right? So we ended up reversing these polarities, drain to source and the gate to source. And then we also ended up using the modulus values of the threshold voltage, right? So modulus values of the threshold voltage, reversing of the polarities, all the equations remains the same. And again, why did we reverse the polarities? Because we saw that rather than giving a positive voltage to the gate electrode, Now we give a negative voltage to the gate electrode to push down all the holes to create a depletion region and subsequently attract the holes from the source and the drain to the channel to induce a P channel for a PMOS. And similarly, the battery is opposite. So it's a source to drain, positive battery. To apply a signal to give a negative voltage to the drain terminal. Right, so this battery, source to drain battery, gives a negative voltage to the drain terminal. Right, so it negative voltage to the drain terminal, and similarly, source to gate gives a negative voltage to the gate electrode. And this is how we can, so that is why these polarities are reversed and why we have a modulus values on the threshold voltage. So using these conventions, you can easily solve all the questions related to the PMOS and the NMOS. I will also upload some of the homework problems, recommended homework problems that you can solve. With that, so before I wrap up, so today we did one quick example. The take-home message of the quick example was before, so if you have those summary slides with all the equations and everything in handy, the most important thing is just to determine where the transistor is being operated, whether it's the triode region and the saturation region, right? Whether it's for the NMOS, so for the first thing is that is the transistor an NMOS or a PMOS, then whether it's being operated in the triode region, the saturation region, or the cutoff region, and then use these formulas to find out all the answer. Most important thing is the concepts, understand the basic concepts, right? So after that, we talked about this very briefly about the subthreshold region, the concept of the subthreshold region, that it is not necessarily that when the gate to source voltage is less than the threshold voltage, the current is 0. When it is very close, the current will start to flow, provided there is a VDS. However, it exponentially increases as it reaches very, very close to the threshold voltage. We talked about the symbol of the NMOS. We talked about the summary slide. We talked about the gate to source voltage and this constant current voltage controlled constant current source, in which based on the gate to source voltage, we can control the current, the constant current provided by the transistor, right? And because we are operating the transistor in the saturation region, and we are going to exploit this thing while designing the amplifiers. We discussed the structure and the basic operation of the PMOS, very similar to the NMOS. Again, the only difference is now you have using complementary and the p-type materials, you kind of reverse those materials, and you now, in order to operate the transistor using exactly the similar methodology or using the similar principles, we have to reverse the polarities. We discussed very briefly CMOS, the symbol of the PMOS, and again over here, in order to operate the transistor, we have reversed the polarity. So our in all of these equations, we have polarities of these voltages reversed, and we have a modulus of the threshold voltage. Okay, so with that, thank you so much for this lecture, and I hope you will review this, all the information, and I will upload the next lecture soon. All right, thank you so much. Bye-bye. Have a good day.